So, level 2 physics, we've gone through voltage, current and resistance in series and parallel. In this lesson, we're going to combine it all in together with something called the potential divider. Because resistors can be connected in a circuit to control the voltage in parts of a circuit. So here we have a circuit here with a system's voltage, Vs, which is the total voltage. So from our previous lessons, what is the relationship between the three currents here? I1, I2, and I3. Of course, the relationship, because it's going to be in series, is going to be the same at each point. So I1 equals I2 equals I3. So, looking at the four voltages, Vs, V1, V2, and V3, what is the relationship between the four voltages? Well, from our previous lessons about voltages in series, we know that they equal the supply voltage. So Vs, which is here, will equal V1 plus V2 plus V3. And how do we find the total resistance in a series circuit? Okay, so we want to find R1, R2, R3, and R total. So that will equal simply the addition of R1, R2, and R3 together. So the R total equals R1 plus R2 plus R3, which you should be very familiar with now from our previous lessons on voltage, current, and resistance in series and parallel circuits. So, if we combine this all together, making sure you can see Vs there, the total voltage of the system, what is the relationship between the four currents here? Total I1, I2, I3. So it's in parallel, so it must mean that the four currents must add to give the total current. So IT equals I1 plus I2 plus I3 because it's a parallel circuit. This is all going somewhere, trust me. Again, parallel circuit. So what is the relationship between now the four voltages? V1, V2, V3, and the total voltage of the system, Vs. Being a parallel circuit, it will be equal to the supply voltage, which is here. So Vs equals V1 equals V2 equals V3. Again, we should know this from previous lessons. And finally, the resistance in parallel. So we want to find R1, R2, and R3. And what is R total? Then again, it's simply 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. So if we combine all this logic together, in a series circuit with two resistors and a power supply, this is known as a potential divider. And potential dividers are very important because they're used in things called potentiometers, which means that you can change the voltage and resistance of a circuit. It's also involved in LDRs and thermistors, which we've already looked at. So a very important concept in physics. So why is it called a potential divider? Well, potential, as we know, is voltage, and what you're doing is dividing the voltage. In a potential divider circuit, a voltage divider consists of two devices, usually resistors, connected in series. And those resistors can either be standard resistors, or they can be rheostats, or they can be light-dependent resistors, or they can be thermistors. So quite useful if you're developing circuitry for, say, ovens or home security systems. And they're always connected in series. So what can we say about the current in a series circuit? Well, current at, say, a resistor equals the voltage at that particular area divided by the resistance. It stays the same throughout, okay? It's the same. That's current in a series. We know that from our previous lessons. So I1 equals V1 divided by R1, which equals I2, which equals V2 divided by R2. So in a voltage divider circuit, I1 equals V1 divided by R1, and I2 equals V2 divided by R2. So we're looking at a diagram like this. It's going to have a resistance R1, a resistance R2, and a voltage 2, and a voltage 1. So what's that saying is that the current going through R1 will equal the current going through R2. So if you're rearranging this, then that means that V1 divided by R1 equals V2 divided by R2, and through a bit of jiggery-pokery, V1 divided by V2 equals R1 divided by R2. So what does this all mean in terms of a potential divider? Well, we have the equation, of course, V1 divided by V2 equals R1 divided by R2. So if the resistance goes up in R1, because V1 divided by V2 equals R1 divided by R2, it means that the voltage, let's do a better job of an arrow, the voltage in V1 also goes up, which means the voltage in the second resistor, across the second resistor, must be going down, because this has to be constant and equal this. Okay, so you can use the equation to calculate the voltages at different points in the voltage divider, potential divider. I'm just going to give you a quick diagram to illustrate what that looks like and what everything is in this diagram. Okay, so you've got a positive voltage, zero voltage. So you've got supply voltage across the two resistor components. Of course, you've got resistor 1 and resistor 2, and you have a V1 and a V2 here, very nicely drawn by myself. So you can use these equations to calculate what the different resistors are at these different points. You have to be wary, of course, because R2 divided by R1 plus R2 is the portion of the supply voltage across R2 of Vs, well, not over, across V2. And voltages in electronic circuits are normally measured with respect to a ground, or 0 volts, and the voltage between the particular point and the ground in a circuit is often loosely said to be the voltage at that point. So that would say be point A, for instance, so you'd be measuring the voltage at that point. That's pretty much all you need to know for potential dividers. There will be some calculations you'll probably have to do, but that's probably enough for today. We'll work through that in the textbook.